this. Okay, we finished the experimental part where we did the measurement. We measured the volume of the trapped air plus vapor on a different temperature. Now we need to calculate its vapor pressure. We need to calculate the vapor pressure of water. Okay, there's two things we need to apply. We need to apply Dalton's law, P total, which is equal to the partial pressure of air plus water. Anytime we have a measurement there at certain temperature, there's two things there. There's the air and there's the vapor from water. The only time we were assuming that's only air, where we go way down to below 5 degrees centigrade. Below 5 degrees centigrade, the vapor pressure of water is negligible or zero. So what we're going to do, we want to find a way to measure the vapor pressure of water at that 80 degree, 75, 70, 65, 60, how are we going to do it? So we're going to apply this B1 V1 over T1 equal B2 V2 over T2. If we determine or find out the pressure of the air at different temperature, then we can subtract that from total, which is the barometric pressure, and that will give us the pressure of the vapor pressure of water. Okay? Got the idea? We need to find a way to measure the pressure of air at different temperature. Okay? And then we take the barometric pressure as our total, subtract that pressure of air from V total, and that will give us the vapor pressure temperature at different temperature. So we apply V1 V1 equal V1 V1 over T1 equal V2 V2 over T2. You know, this is a combination of the Charles law, Boyle's law, and all. Okay. So what for this one, I picked those numbers here. I'm gonna determine, and I just did it for one calculation, the pressure of air at 80 degrees centigrade. Now V1, I'm gonna assume that's only air, and volume was 405, and temperature was 3.2 here. So B1 V1 over T1 equal B2, which I don't know. Temperature here was 80, volume was 9.6. If you notice here, I haven't changed any of those, you know, to a liter or anything. I just kept them on milliliter because milliliter here, cancel here, Kelvin here, Kelvin here. At the end of the day, you will have your pressure in millimeter mercury. Okay, so if I determine, if I do this, so actually, let me circle this. So actually this value is the same for every measurement, right? When you do that, the only thing will be changing in this and this, right? Because this is the same V1 equal for air. So this is, and this will be changing. You do the math, you come out P2 here, 398.6 millimeter mercury, and actually what this is P air at 80 degrees centigrade. Now I go to P total, which is my barometric pressure, because all of them under atmospheric pressure, 739.25 equal P air, which is 398.6, and I get P water here, 340.6. That's my first measurement, and that's only I did 4. Now you convert this to atmosphere measurement, so divide by 760, 1 atmosphere equals 760 millimeter mercury, because all your measurement has to be in atmosphere. Okay, you convert to divide by 60. And first thing, you have your T water, what was the temperature? Then you have 1 over T water in Kelvin. Now, let me tell you this, otherwise you might run into a problem. When you do your 1 over T, at least take at least 4 decimals. You know, you can actually take 273.02 decimal. Because if you take the less than that close, then the numbers, when you try to plot it, is not going to be, you won't be able to, so take 4 decimals. There the numbers are very close. You see, like here, first example, first one, 0.002831, 0.02872, 0.02914, 0.0, okay? So be sure that 1 over t take at least 4 decimals. Okay, so you can be able to, okay, now I already got my, got my V water in millimeter, I convert it to atmosphere, and I got 1 over t. This is my linear equation here. This is the linear equation here. Natural log P, so you need to find the natural log of P, and it will be negative, that's fine. Equal minus delta H R over T. What is the variables here? And this is a good question. Which one is the variable here? T is what we were changing. What we were changing, temperature and volume, but in this equation, the temperature is the changing. So you plot, if you plot 1 natural log B over 1 over T, you get a straight line. Because this is equation of a straight line, right? See it, see it. Y equal mx plus c. Okay, now to solve the problem you have, once you get this equation here, once you get your linear equation would be something similar to this. Your y equal minus 5,680.8 x and plus 15.0, for example. Now, to find delta H, you have to look at this linear equation and look at your, so what's the slope here? This is your slope, guys. This is your slope. So your slope actually, minus 5680.8 equal minus delta H over R, and you know the value of R, and then you get delta H, right? Confusing? Not clear? No? Not clear? I go and find the slope. My slope from my linear equation equal minus 5,680.8. What's the slope equal? The slope equal minus delta H over R. R equal 8.314 kilojoule per mole, and you multiply that and you find delta H. Now, how to find delta S? Delta S over R, that's the intercept. That's what equal 15. And everything is, everything is done.